All right, so what I'm going to do here is I'm going to go through and I'm going to do the first problem in each of these series of problems. So each of these types of categories follow a very similar format in terms of how to solve. So we start out here and we want to know the representative particles of each of the following. So we want to know how many atoms of gold are in 2.15 moles. So again, the first thing that you always do is you write down what is given. So we have 2.5 moles of gold. Remember, the symbol for gold is AU. We set up that conversion factor. We cancel same units on the diagonal side. So we're going to put moles of AU. And then the representative particles for a gold is going to be atoms. So we put this atoms. Going to give a little bit more space here. We put atoms. And then remember, one mole here is equal to 6.02 times 10 to the 23rd particles. Okay? So 1 mole is equal to 6.02 times 10 to the 23rd atoms of gold. So my calculator, what I need to do is this. I'm going to take 2.15 times 6.02 times 10 to the 23rd. Now it's important that you put parentheses around anything with scientific notation. So our answer here is 1.29 times 10 to the 24th atoms of gold. Okay, now B and C follow a very similar type of format. Just remember, nitrogen oxide, that's going to be molecules in terms of the representative particles, and potassium bromide, that is going to be formula units. All right, moving on down to number 2. It says calculate the number of moles in each of these particular representative particles. So we always start out by writing down what is given. So we are given 8.92 times 10 to the 23rd atoms of barium. And we go ahead, we put atoms on bottom, and we can go straight to moles of barium. Okay, now remember from up top here, there's 6.02 times 10 to the 23rd particles in every 1 mole. So that means 1 mole is associated or equal to 6.02 times 10 to the 23rd. So what we need to do is this. We need to make sure, first off, we have parentheses around our scientific notation, and we put this in our calculator. 8.92 times 10 to the 23rd. And I need to put a set of parentheses myself. And so this 8.92 times 10 to the 23rd gets divided by 6.02 times 10 to the 23rd. I press enter. Rounding to 3 total digits, I get a value of 1.48, and that is 1.48 moles of barium, Ba. Now, B and C once again follow a very similar format to be able to go from these representative particles to moles. Okay, moving on here to our next set of problems, our next page of problems, we get to this. We want to determine the mass in grams of the following. So we start out here with 1.24 moles of beryllium. So we have 1.24 moles of Be. Be is the symbol. We set up the conversion factor here. We can go from moles of Be to grams of Be. Okay, where do I get those numbers to find the number of grams per mole? Well, I look on the periodic table. I found Be. I round to 2 decimals. So I'm going to round to 9.01. And so that is 9.01 grams per mole of Be. The 9.01 number is associated with G for gram, so this becomes 9.01 grams per 1 mole. So to calculate this out, all I'm going to do is take 1.24 times 9.01. I press enter. Rounding here to 3 total digits, I get a value of 11.2 grams of Be. So 11.2 grams of Be. B and C follow a very similar format. Just remember, we have different elements, so you're going to have to utilize the periodic table to determine what their mass is. All right, moving on to number 4. We're going backwards. We want to calculate the number of moles in each of the following. So we have 6.35 grams of lithium. Again, you always start out by writing down what is given. So 6.35 grams of lithium. The symbol for lithium is Li. And then units diagonal need to cancel out, so we can get to grams of Li. And on top, we get to moles of Li. So we turn to our periodic table again. We find Li. We round to 2 decimal places, so 6.94, and that is 6.94 grams per mole of Li. The 6.94 number is associated with grams, so in this case, it's going to go on bottom, and that is for every 1 mole. We then, in our calculators, take 6.35 and divide it by 6.94. We press enter. We round to 3 total digits, which will be 0.915. So that is 0.915 moles of Li. Again, B and C follow very similar formats. The only difference is we have different elements in this case. Okay, moving right along here, moving on to the first example in number 5. So number 5 here, it says how many atoms are in the following sample. So I will tell you this is a 3-step conversion. So for our 1.24 grams of cobalt, we start out and we put 1.24 grams of cobalt. The symbol for cobalt is CO. We then need to cancel our units diagonal, so we have grams of CO on bottom. And we can't go straight to atoms. We have to first go to moles. So gram over mole, whenever you see that, you turn to the periodic table. Cobalt, if you look here, has a molar mass of 58.93. So 58.93 grams per mole of cobalt, CO. The 58 number is associated with grams, so it's going to go on bottom. So 58.93 per 1 mole. We are not an atom, so we need to do another conversion. That means we cancel out moles of CO. And now, once we go cancel out moles, we can get to atoms of CO. So now, every 1 mole, and this hopefully should be pretty standard, every 1 mole has 6.02 times 10 to the 23rd atoms. Okay? So in my calculator, what I'm going to do is I'm going to multiply everything on top, divide it by everything multiplied together on bottom. So I'm going to put 1.24 times 1 times a set of parentheses, 6.02 times 10 to the 23rd. I press enter. Now I divide that number by everything. Make sure you start out with a parenthesis, everything on bottom. So 58.93 times 1. I press enter, and I get a value of 1.27. When I round, 1.27 times 10 to the 22nd atoms of cobalt. So again, this equals 1.27 times 10 to the 22nd atoms of cobalt, CO. And that would be our answer. Now, Problems B and C follow a very similar type of format. The only difference is, again, they are different elements, so that molar mass is going to be different. Okay, moving on here. We want to, it's a little bit different for number 6, we want to calculate the number of atoms in each element. So I will say this, it's going to be kind of tight, kind of squeezed in this position here. So what we do here is this. We want to know the number of atoms of each element in aspirin, this formula right here. So we start out and we have 3.35 moles of aspirin. So C9, C9H8O4. Then we need to cancel out moles of aspirin. So moles of C3H8O4. And we need to go to moles of carbon initially. Now, how we find the number of moles of aspirin to the moles of carbon is by doing this. We look at our chemical formula and we say, hey, in one of these things, in one aspirin, so one aspirin, there's how many carbon? Well, there's 9. So there's 9 moles. And then we multiply this, our number of moles of carbon, by the value of atoms of carbon. So remember, there is 6.02 times 10 to the 23rd atoms per 1 mole. Okay? So what we do in our calculator, again, multiply everything on top, divide it by everything multiplied on bottom. So 3.35 times times 9 times 6.02 times 10 to the 23rd. We press enter. We get a value, when we round, 1.82 times 10 to the 25th atoms. 1.82 times 10 to the 25th atoms of carbon. Now, I'm going to squeeze the next one right below this, and I'm going to try to find out, well, how much in atoms do we have, or how many atoms of H do we have in aspirin? So we start out by 3.35 moles of aspirin, so C9H8O4, times 1 mole of aspirin, C9H8O4, has how many moles of H? Well, you look to that formula. There is 8 in that formula, so that means there are 8 moles of H in every mole of aspirin. Then we take our moles of aspirin and we multiply it by Avogadro's number. So 6.02 times 10 to the 23rd moles of, atoms of H. Okay, so we then do this. We take 3.35 times 8 times 6.02 times 10 to the 23rd. We press enter. Our value for our number of atoms is 1.61 times 10 to the 25th. And that is 1.61 times 10 to the 25th atoms of H. Now, this one's going to be really squeezed here, but we're going to do this for oxygen. So we start out here with 3.35 moles of aspirin, C9H8O4. We cancel out on bottom our moles of aspirin, C9H8O4, to our moles of oxygen. Again, the moles of oxygen is just the number or the subscript behind oxygen. So that is 4 moles of oxygen. And then we multiply that value by Avogadro's number. Okay, so we multiply it by 6.02 times 10 to the 23rd atoms of O. Okay. We press in our calculators 3.35 times 4 times 6.02 times 10 to the 23rd, and we press enter, so we get a value and we round. 8.07 times 10 to the 24th, 8.07 times 10 to the 24th atoms of O. Okay, I know that's kind of squeezed in here, but the key thing is 1 mole of aspirin is equal to the number of moles of individual elements seen by that subscript. All right, one more example problem I'm going to do with you guys, and that is finding the molar mass. So the molar mass here of formic acid. First off, the formula is CH2O2. So we list everything out. So CHO. Then on the periodic table, what we do is we find carbon. We find the molar mass to be 12.01 grams per mole. So we do 12.01 grams per mole times the number of carbons we have. We have 1 carbon, so that means that this equals 12.01 grams per mole. Then we have H. We look up H. Now H is the weirdism. I like 3 digits on H, or 3 decimals. So the value for the molar mass is 1.008 grams per mole times how many H's? Well, we have 2 H's. So if you multiply 1.008 times 2, so 1.008 times 2, we get a value of 2.016. So that's a value of 2.016 grams per mole. Then oxygen, we do the same thing. Look on the periodic table. It rounds when you do all the rounding to 16.00. So 16.00 grams per mole times how many oxygens? Well, we have 2 oxygens. If you do 16.00, so 16.00 times 2, that equals a value of 32.00 grams per mole. Last step here is add everything we see. So we're going to add our values here. So we take 12.01 plus 2.016 plus 32.00. We press enter. We round to 2 decimals. So this rounds to 46.03 grams per mole. 46.03 grams per mole in formic acid, or CH2O2. All right, the problems I did not do, those are ones that you need to complete. Again, the problems that I did not do or left blank are the ones you need to complete.